Okay, I hope it fits everything. I hope showed. This one is called alpha. Let me put it down a little bit. Okay, so this is the recursive equation again. And realize it, when you unfold it, we just use this 1 plus HM3 all the time together, so I'm going to simplify, call this R, alpha. In this step here, I'm trying to unfold this one over and over so that we relate Gn, the final gap, with the very first gap, G0. So let's apply this one. You see the index, the k plus first gap and kth gap here. So if I start from nth gap, this must be n minus 1 n minus first gap. So this is called alpha. So just Gn minus 1, h squared m2. So we have this one. The next step is that you replace this one with the larger possibility. So you apply this recursive equation in here to Gn minus 1. So this is Gn minus 1. One before would be Gn minus 2. So that part is replaced by the larger possibility, which is written here. This alpha and h squared m2 is out there, and this Gn minus 1 is replaced by this Gn minus 1 is this whole thing again, alpha times Gn minus 2 plus h squared m2. That's what you see over here. So we're going to simplify as much as we can, which is this one here, alpha squared multiplied to Gn minus 2, and there's h squared m2, h squared m2. So if you factor that out, you can see that alpha is multiplied to h squared m2, and there's nothing multiplied to h squared m2, so altogether must be alpha plus 1. In the next line, I'm replacing this Gn minus 2, that's the only gap that's appeared in this part, with this Gn minus 3 again. Here's Gn minus 2, so there's Gn minus 3. So Gn minus 2 here is replaced by this whole thing, which has appeared here. Alpha times Gn minus 3, h squared m2. Okay, now if you expand it and simplify, we have alpha cubed multiplied to Gn minus 3, and collect all the h squared m2, there's r squared multiplied in there, and alpha plus 1, it was not r, it was alpha squared plus alpha plus 1. So I encourage you to actually unfold a couple more times, convince yourself on how this one actually looks like, but inductively we can show the following. The Gn, so here's what you notice, the power that keeps increasing in this part in here, and then if you look at the index, this is kind of complementary, and if you add this 3 and this index you see down there, that's always n. If you see this index here is alpha squared, and index down this n minus 2, they're always n. As this one increases, exact same amount, this one decreases. So if I see alpha to the n, and that must be 0, so that these two adds up to n. And when it's alpha squared, we start from, in this part, alpha to the first. When this one is alpha to the third, we start from alpha squared. So if this is alpha to the n, we must be starting from alpha to the n minus 1 and go all the way down to 1, and with this creating this one. And think about what this n is. This n is a number of interval we are dividing. The interval 0 to beta. So if we put more and more interval into that, to decrease this gap Gn, this will increase more and more terms. So this is very, very subtle bound here. So if nothing crazy happens in this sum, and then we're in good shape. This h will kind of kill this one h, since h is the interval between this xk and xk plus 1. It's approaching 0 as long as this is under control. And this one, you have to think about it, what happened to the alpha n, alpha to the n. So right now, it's unclear that whether this is going to give us a good bound so that we can conclude that Gn approaches 0. But let's calculate this part. And this part is known as a geometric series. And you might have learned this in Calc 2. So here's a closed formula, although there's dot, 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 there's n terms involved in here. N terms of the geometric series can be simplified into following closed form. It's alpha to the n, that n is usually coming from number of terms in the geometric series, and alpha is a common ratio between these adjacent terms. So it always ends up like this. So let's go back to what alpha is and simplify alpha minus 1 and think about what this alpha to the n is. Alright, here's the first bit of it. If you go back, and turns out it's alpha was that coefficient of a gk. So that was 1 plus h times m3. So we see alpha minus 1 down there, so alpha minus 1 will be h times m3. So that will be replaced by h times m3. It's nice. Let's now think about alpha to the n. Here's the first step toward it. Alpha to the n, alpha is replaced by this 1 plus hm3. What was h? And h was this beta, the interval, length of interval of our problem, 0 to beta, divided by n. And we're increasing this n, therefore h times m3 is approaching 0. Now, this must have reminded you of some interesting indeterminate form you might have learned in Calc 1. 1 plus small quantity, that's almost 1, raised to high power. If this is almost 1, raised to whatever power is try to be 1. If it is slightly greater than 1, if you raise to a high power, you know it's going to go to infinity. So it's two different forces through behavior, so it's indeterminate form. So here's some reasonable thing we can do here. So if this is going to be called t, and so I'm replacing this substituting hm times m3 with a t, and we use this result, 1 plus t raised to the 1 over t approaches 0. So let me write down it over here. Okay, I wrote it there. What I'm talking about is the standard definition of e. The way the e is defined historically, I think, is that this 1 plus t raised to 1 over t. If t approaches 0, that 1 over t is kind of going to infinity. So this one converges to 2.712 and that number. So by looking at it here, it might trigger that looks a lot like this one. So why don't we change that into that form? So I called hm3 to t and try to write n in terms of t here so that we can pull this form out of it. So what's n here? N is beta divided by h. That's why you see that part here, beta divided by h. So let's write h in terms of t. So here it is, and h is, and 1 over h is m3 divided by t. So here's, and beta is out there, and 1 over h is replaced by m3 divided by t. So if you group it like this, we pull out as 1 plus t raised to 1 over t, that part in here. So as h approaches 0 or n approaches infinity, we know what happened to this quantity. Namely, it approaches e to the m3 beta. So this whole quantity, alpha to the n, actually is a nice nice convergence point. That's very subtle here. That didn't go to infinity or anything. It's settled into e to the m3 the beta. And because of alpha minus 1 is calculated here, if after we deal with this one, you will see this one have a very nice bound as well. So it's a very subtle calculation. So let me show you this part once again. This was our final kind of estimation, the nth gap in terms of the first gap here. There's 0 beginning gap, G0, and alpha to the n. We estimated that. Let me move this one over here. I hope you can still see it. Alpha to the n was approaching, so let me move it all the way down here. That's better. Okay, here it is. Alpha to the n is approaching e to the m3b, so that part alpha to the n is approaching this number. And alpha minus 1 was hm3, so that part will be replaced by hm3. And alpha to the n is again replaced by m3. So here's the comparison. So gn is alpha to the n is replaced by that exponential value, and h squared m2, and alpha minus 1 is replaced by that hm3, it's down here, and alpha to the n is replaced by this exponential value again. So I shifted a little bit, and let me show you the next line. Here it is. I kept this first term is exactly what it is, and there's h and h cancel, so we have only one copy of h, and this m2 and m3 is just a constant, and this is another constant, an exponential. So only thing that varies as h approaches 0 or n approaches infinity is this h part. So this part becomes 0. And the very first gap, if you think about the box, is the very first point is z0 minus y0. We started exactly that point, so that value is exactly 0. So therefore, it proves that the final limit, as you put more and more points in between 0 and beta, approaches 0 in here. So that's the conclusion of the proof.